into sort of a geometric understanding of, how to sort of reflect points from one side of the boundary to another. Okay, so to start with, I want to consider a boundary value problem, okay, that is a simpler version of Poisson's equation, u prime prime equals f, and we'll put it on a bounded domain. And we're just going to give ourselves homogeneous boundary conditions. Okay. Am I coming through all right? Is my internet cutting out?
Yep, you're good.
Okay. All
Yeah,
right.
it was just that one time.
Getting weird warnings on my screen, but I guess I'm okay. Okay. So how do we solve this, right? Well, we can solve it, okay, by just integrating twice, right? This is just a one-dimensional problem. It's just a second order ODE. I have the two boundary conditions that I need in order to specify it, right? So if I integrate once, right, then I get minus u prime is equal to the integral from 0 to x of f of y dy plus some constant, right, which would be my u prime of 0, but I won't go ahead and plug that in yet, right? And then if I integrate again, then I get minus u of x, okay, is equal to the integral from 0 to x, integral from 0 to z, f of y, dy, dz, okay? And then I have these trailing factors, cx plus d, right? So I need to specify those, okay? If I apply my boundary conditions now, I have u of 0 is equal to 0, okay? And so that means that 0 is equal to d, right? So I get d equals 0. U of 1 now is equal to 0. This gives an equation for C, okay? So, so first note the following, right? I can write u of x is equal to minus the integral from 0 to x, integral from 0 to z, f of y dy dz minus cx, okay? So what I can do, right, is I can swap the order of integration in this case, okay? And so let's think carefully about how this is done, right? So if I have here, right, let's say this is y and this is z here, okay? And I already messed things up, I hope not. Okay. Okay. So this is y and this is z here, okay? And what I'm saying is I'm going to integrate from 0 up to z here, right? Because this is the line y equals z, okay? And then I'm going to integrate z from 0 up to x, right? So that means that I have this right triangle that gets integrated over, right? So this is my right triangle that I get integrated over. So this two-dimensional integral, right? I integrate from 0 to z in y, and then I integrate z from 0 up to x, okay? All right, so I got that right. But now let's say I want to switch the order of integration. Let's say I wanted to integrate with respect to z first, and then I want to integrate with respect to y, okay? Well, if I did that, then I would integrate from y up to x first, and then I would integrate y from 0 to x. Okay? Maybe you remember doing this back in, I don't know, Calc 2 or Calc 3 or something like that. Anyway, it helps to draw these pictures when you're doing this. Okay. So what do we get? So we get the integral from 0 to x, okay, and the integral from y up to x now, okay, f of y dx, sorry, dz, dy, and then I still have this trailing minus cx. Now, why is that helpful? Well, because f here now is a function of y, so I can integrate once already, because there's nothing involving z on the interior. So I end up with minus integral from 0 to x minus y, f of y dy. Okay. Still, I have a minus cx here. Okay. All right. So that's good. Okay. So that means that at u of 1 equals 0, okay, this implies that c is equal to minus the integral from 0 to 1 of 1 minus y f of y dy. Okay. So I now have an expression for my constant, but it's just in terms of this integral that's involving my unknown function. Okay. Now we're going to put this all together, right, to get our function. But you already see that I've done things in a way such that this is kind of like a convolution, right, of my right-hand side, okay, against just a function. It's a very simple function, right? It's a linear function here, okay? What I would like for this to kind of be in this Green's function formulation is for this integral not to be an indefinite integral, right? But I'd like it actually to be an integral, a definite integral over my whole domain, because that would make it much more like a convolution, okay? And then I would have boiled things down to my inhomogeneity, some Green's function, and then just a straight convolution like that. Okay, so let's see if we can get things in that form. So it's going to take just a few steps. Okay, so the next step then, okay, is that I have u of x is equal to now the integral from 0 to x, y minus x f of y dy. Okay, and then remember I had my my c of x here. So what was my c here was a minus. I had a minus c of x. So now I can just multiply this whole thing by minus x, and I get something that I'm going to add on, which is plus the integral from 0 to 1. I'm going to pull the x inside, 1 minus y f of y dy. Okay. Then am I okay? Yeah, I think I'm okay. Okay. So the next thing I'm going to do, okay, is I'm going to take this, I'm going to take this part here and I'm going to split off the part from 0 to x, and I'm going to combine it with this part here, okay? So that means I'm going to have just a y part, and then I'm going to have a yx part, but the just x parts are going to cancel. So I get the integral from 0 to x of y times 1 minus x f of y dy plus the integral from x up to 1 x 1 minus y f of y dy. Okay. And so what I have, right, I have a separate integral from 0 to x and x to 1. So I can actually just define a piecewise function now that is defined from 0 to x and from x to 1. This is my Green's function from 0 to x. This is my Green's function from x to 1. And then I have, lo and behold, a singularity at x, right? Which is where I should expect my singularities to be, okay? Because then when I differentiate them twice, even though it's continuous, right? I'm going to have a jump discontinuity, and then I'm going to have a delta function when I differentiate it twice. And hearkening back to the fundamental solution for the heat equation and the fundamental solution that we did for Poisson's equation, I should expect that when I differentiate this twice, I get a delta function. So I pull out the unhomogeneity in that case, okay? So I can finally write this as the integral from 0 to 1, g of xy, f of y, dy, and this is defined from x goes from 0 to 1. And what's my Green's function? I'll write it down and then I'll draw it, okay? And then we'll kind of take a pause. When, let me make sure I get this right. Y is from 0 to x, then we have y times 1 minus x. When y is from 0 to 1, okay, then I get x times 1 minus y. And so what does this thing look like? Okay, so for g of xy, okay, if I freeze x and I'm plotting this as a function of y, and here's 1, and then here's x here, okay, my Green's function is going to look like this, okay. So on this, on the upstroke, right, I have y times 1 minus x, okay. And on the sort of downstroke here, I have x times 1 minus y, okay. And they meet together. It's continuous, but there's this kink that when you differentiate it twice, you get a delta distribution. So you get a singularity, okay. So again, for a Poisson equation on a bounded domain, I can get this Green's function by hand, okay? Questions about this? Okay. I think I have a minute left in class, so I will push the explanation of everything that comes next to the recorded lecture. So the recorded lecture, I'll finish off all this discussion of Green's functions, and I may get some into test functions and distributions, giving us a little bit of a firmer functional analysis footing for you know, how to handle distributions. We've sort of bandied them about a bit, but there's a more careful way for handling distributions than we've handled them so far. And then yeah, probably we'll try and wrap up next week more